Yes, sir. You can start now, sir.
Okay, ma'am. Can you make me the host of this session, ma'am, so that I can start sharing my screen? Okay,
Yes, sir.
ma'am.
Done, sir.
Thank you, ma'am. Thank you. So, students, good evening, all. Now I am sharing my screen actually. So, for the past few classes, we were discussing the different kinds of concepts related to point charges. Okay, so today we are going to discuss the continuous charge distribution. So actually, whenever we talked about the point charges, so we actually describe the charges at the microscopic level. So whenever we talk about point charges, what we actually mean is that the charges actually not visible to our naked eye, or we actually talk only in terms of the microscopic level only. Okay, so at the microscopic level, it is reasonable or it is sensible to talk about the point charges. But at the macroscopic level, okay, whenever you see a body or whenever you see an object, there is a continuous distribution of charges in the object. Okay, so because whenever you see the objects with your naked eye, you won't be able to differentiate, or you won't be able to see the different point charges present in the object. So at the macroscopic level, when we are talking about the charges, what we actually mean is the continuous charge distribution. Okay, so at the macroscopic level, whenever you take a piece of paper or whenever you take an iron rod or something, so there the charges are distributed continuously. Okay, so in that case, we should consider discussing the continuous charge distribution. So so yes, whenever we take a macroscopic object, what we can say is that this much of charges is present in the particular area of the object, or this much of charges is present in the particular volume of the object, like that. Okay, so this is what a continuous charge distribution is all about. Okay, so now at the macroscopic level, when we discuss the continuous charge distribution, there are actually three types of continuous charge distribution, what you can see in a macroscopic object. And here on screen, you can see the different types of continuous charge distribution. Okay, so so here when you see this one-dimensional rod, or a long wire, okay, a long charged wire. So what I am pointing out in the figure is a long wire and a charged wire also. Okay, it is a uniformly charged wire. So in this uniformly charged wire, there's a particular quantity called linear charge density. Okay, the particular quantity is called linear charge density. So what is meant by linear charge density? So as far as this wire is concerned, so linear charge density so this means the charge divided by the total length. Okay, the charge divided by the total length, that is called the linear charge density. So here this lambda is actually the linear charge density here. Okay, so this lambda, what you can see in this picture, this lambda, this is the linear charge density or charge per unit length, which means when the length of the wire is, for example, 12 meter, and you have 48 charges in this 12-meter length, the linear charge density will be 48 divided by 12, that is 4. Okay, which means when you take 1 meter length of this wire, in that 1 meter length of the wire you can find 4 charges. That is called linear charge density or charge per unit length, which means in 1 meter length you can find this much of charge, that is lambda amount of charge. That is called linear charge density or charge per unit length. So that is called linear charge density. And whenever you want to find the small amount of charge dq in this wire, okay, you take a small portion of the wire as dl. Okay, for example, here I am marking, this is the small portion of the wire. Okay, so when you take a small portion of the wire of length dl, then the total charges present in this small portion. Okay, here I am marking, so this portion, so this portion of the conductor, let me take as dl. So when you want to find out the total charge present in this small portion of the length, that is dq equal to lambda into dl. That means lambda is nothing but charge per unit length. When you multiply this charge per unit length with the small element of length dl, you will get the total amount of charge dq in this small element of length dl. Okay, so dq equal to lambda into dl. So this amount of charge is present in this small portion. So when you want to find out the electric field at this point P, which is at a distance r from this small element of length dl, okay, then you have to integrate this equation, or not integration, actually the small amount of charge is given by dq, and then you have to apply the electric field formula. So there, when you want to apply the charge present in this small element of length, then you have to use this dq. Okay, so this is the linear charge density or charge per unit length. The second case here, you can see a sheet of charge. Here what we have to talk about is the surface charge density. Okay, the surface charge density. So what is meant by this surface charge density? This is nothing but charge per unit area. Okay, so charge by area. So this is actually represented by sigma here. So that means in 1 meter squared area, how much of charge you are having. That is called sigma, or the surface charge density. So here they have given you a small amount of area. Okay, this area marked in red color, right? The small amount of area is taken as dA, and whenever you want to find out the small amount of charge in this small area dA, then dq equal to sigma into dA. That means sigma is nothing but the amount of charge present in 1 meter squared area, and when you take a small area dA in this sheet of charge, then you will be having sigma into dA amount of charge in this area. So that is represented by dq, that is surface charge density. And here the third type is volume charge density. Okay, so in this diagram, the volume charge density is actually represented as q, but in many books the volume charge density is represented as rho. Okay, in many books. So rho is nothing but charge by volume. Okay, rho is nothing but charge by volume. That means in 1 meter cube volume of this object, you are having rho amount of charge. Then when you take this dV amount of volume in this material, then the charge present in this dV amount of volume is dq equal to rho into dV. Okay, here in this diagram they have represented the volume charge density as q, but otherwise in many books the volume charge density is represented as rho, so that the small amount of charge present in the dV amount of volume is dq equal to rho into dV. So in dV amount of volume, you will be having this much of charge, rho into dV, that is charge into this volume. So volume charge density rho equal to charge by volume. So like this, you can understand the different types of continuous charge distribution. I hope it is clear to all of you. Okay, the linear charge density, the surface charge density and all. So all the different types of charge distribution I have explained you. So I hope you all understood it clearly. So even if you have any doubts, you can ask your doubt. Okay, you can unmute yourself and you can talk during the session. Okay, right. So this is what a continuous charge distribution is all about. And then we are moving on to the next topic, that is Gauss law. So what is meant by Gauss law actually? So this Gauss law actually gives the relation. Okay, this Gauss law actually gives the relation between the flux and the total charge enclosed within a surface. So this is what Gauss law is all about. It gives the relation between the total electric flux and the total charge enclosed within the surface. Before proceeding further, can anyone tell me what is the meaning of electric flux? We have already discussed that. Can anyone tell me? Yes, tell me.
So it is the number of electric field lines passing normally to a given surface.
Yeah, you are right. You are right. Very good. So the student has given the exact definition of the electric flux. So the Gauss law gives the relation between the electric flux and the total charge enclosed within the surface. So the form of this Gauss law is this thing. Okay. So phi equal to integral E dot ds, that is equal to Q enclosed by epsilon naught. So that means the charges enclosed within the surface divided by epsilon 0. So this is applicable only when the charge distribution is present in vacuum or air medium. Okay. So when you have any medium other than air or vacuum, then this epsilon naught is replaced by epsilon. Okay. So this phi is the symbol for electric flux, and this electric flux is given by the closed integral of E dot ds. Okay, the closed integral of E dot ds, that is equal to enclosed charge. What is mean by enclosed charge? So whatever surface you are considering around the charge distribution, so that surface should enclose the charge. Okay, so actually whenever you want to find out the total flux or the total electric field due to a charge distribution using Gauss law, you have to imagine a surface. Okay, you have to imagine a surface surrounding that charge distribution. So that surface is called Gaussian surface. Okay, so that surface is called Gaussian surface or Gaussian surface. So whatever way you can pronounce, Gaussian surface. So that surface is actually the surface which encloses the charge distribution, and the charge enclosed should be within this Gaussian surface. So the total electric flux can be calculated by imagining a Gaussian surface around the charge distribution, and then using this relation you can calculate the electric flux. Right. So now we are going to discuss some of the properties of this Gaussian surface. Okay. So here it is. What is meant by a Gaussian surface? So it is nothing but a hypothetical surface. Okay, this kind of surface doesn't actually exist, but we actually imagine a surface around the charge distribution for which the electric flux is to be calculated. Okay, so this hypothetical surface should also be a closed surface, and that Gaussian surface, how you should choose the Gaussian surface. So it should be symmetric with the symmetry of electric field. Okay, that means you can take the Gaussian surface in such a way that the electric field, it should be either perpendicular or parallel to the surface. Okay, that means it should be symmetrical with the symmetry of electric field. So this is the condition to apply this Gauss theorem or Gauss law. The Gaussian surface should be a symmetrical surface, and the electric field, whichever you want to calculate using the Gauss law, it should be either perpendicular or parallel to the surface which you are taking. Okay, so that's why they have given this thing. Okay, this angle between the electric field and the surface area vector should be 90 degrees or 0, like that. Okay, so then only you can use the Gauss law. Okay, right. This is what Gaussian surface is all about. And now actually using the Gauss law or Gauss theorem, what we are going to do is we are going to calculate the electric flux coming out through one face of the cube. You can see the diagram in the slide. Okay, you have a cube and you have a point charge q placed at the center of this cube. Okay, placed at the center of this cube. The side of this cube is actually small a. Okay, the side of this cube is actually small a. So the point charge is kept at the center of the cube. As you can see from the diagram, it is exactly placed at the center. Okay, it is exactly placed at the center of this cube, right? So now what is the total electric flux coming out from one face of the cube? So now let me ask you a question. Totally, how many faces are there in a cube? Okay,
6, sir.
totally 6. So here actually you have to imagine the cube in a three-dimensional view so that you can imagine the 6 faces, okay, of this cube. So as per Gauss law, the total flux, okay, the total flux is given by integral E dot ds. Okay, so integral E dot ds is equal to q enclosed divided by epsilon 0. Okay, so that is the total flux. E dot ds is nothing but the total flux. So the total flux is actually equal to 1 by epsilon naught times the net charge enclosed within the surface. Here you have 6 faces. So the total flux coming out through all the 6 faces is now given by q by epsilon 0. So this is in line with the Gauss theorem or Gauss law. So the total charge enclosed is q, and when you divide it by epsilon 0, you will be getting the flux coming out through the 6 faces of the cube. Okay. So once again, you all know very well the cube is a highly symmetric shape or a highly symmetric array, a highly symmetric figure actually. So here you have 6 faces, and through all the 6 faces you are getting this much of flux in total. Okay, q by epsilon 0. So for a single phase, what is the flux linked with it? Okay, that is, you have to divide this total flux q by epsilon naught by 6. So here q by 6 epsilon naught. Okay, so this is logically simple. So you have totally 6 faces of the cube, and q by epsilon naught is the total flux coming out through the 6 faces of the cube. And here with each face of the cube, you can see you will be getting q by 6 epsilon naught as the flux. Okay, coming out through each face of the cube. So this is the first example which we have discussed now, and now we are moving on to the next thing, the next example actually. So let me erase this first so that it won't be confusing to you. Okay. So otherwise, it will be confusing to you. The annotations of the previous slide will confuse you. Okay. So the next example you can see here. Here you can see a charge capital Q is placed at a corner of a cube. So here, this one, right? Capital Q. A charge capital Q is placed at a corner of a cube. So this is a cube, and you have this charge at the corner. Okay. So the charge is now placed at the corner. Find the electric flux through the 6 faces of the cube. This is your question. So now we are going to work with it. So you all know very well, by Gauss law, the total flux through the cube is Q enclosed or Q inside divided by epsilon 0. Okay. This Q inside is nothing but the charge present within this cube. So this is the general notation. The charge whichever is present inside the cube, that is Q inside. Okay. Divided by epsilon 0. This is the total flux coming out through the cube. Now, here the charge capital Q is kept at one corner. Okay. One corner. So you can't just take the charge inside as capital Q simply. Okay. Because here the charge is kept at the corner. So totally there are 8 corners in a cube. Okay. Totally there are 8 corners in a cube. So since this charge is present at one of the corners, it makes only 1/8 of the contribution to the charge inside. Okay. That means when you take the value of charge inside, it is Q by 8 because it is at the corner. Okay. It is at the corner. There are totally 8 corners. So there are totally 8 corners. So since it is present at the corner, whenever you want to describe the charge present inside this cube, it is actually Q by 8 because of the fact that there are totally 8 corners in the cube. So inside charge means it is actually Q by 8. Okay, this charge makes contribution of 1/8 only. So the charge inside is Q by 8. So this is the total charge enclosed within the cube. Now what is the total electric flux through the 6 faces of the cube? Totally, okay, total electric flux through the 6 faces. It is Q by 8 epsilon 0. Why it is Q by 8? So according to Gauss law, actually I have to change this pen here. So according to Gauss law, the total flux is given by phi equal to Q by epsilon 0. Here the Q is nothing but Q by 8. Okay, Q equal to Q by 8. So when you replace this Q by capital Q by 8, that will be Q by 8 epsilon 0. So since the charge is present at the corner, you will be getting Q by 8 epsilon 0 as the electric flux through the 6 faces of the cube. Okay. So this is the next example which we have discussed. So you can easily remember all these cases, right? So you can take the 2 examples as 2 cases so that you can remember the final result, that is the total electric flux passing through the cube. In first case, when the charge is present at the center of the cube, okay, it is actually Q by 6 epsilon 0. Okay, Q by 6 epsilon 0 in the first case, and now it is Q by 8 epsilon 0 when you have the charge at one of the corners. Okay, so you can easily remember these results so that whenever there is a numerical problem related to it, you can straight away apply this final result and get the answer. Okay, right. And now we have discussed the two examples. Now we shall move on to the applications of some of the applications of Gauss law. Okay, some of the applications of Gauss law. So we have discussed already that the Gauss law gives the relation between the electric field and the total charge, right? The electric field and the total charge. So integral E dot ds equal to q by epsilon 0. So now using that Gauss law, we can actually calculate the electric field of certain objects. So the first application is electric field strength due to this long charged wire. Okay, so this is the wire actually. So this is the wire. Okay, in violet color, in which you can see positive charges. So actually the charges can also be negative, but conventionally whenever we discuss about charged bodies, they actually take positive charges only. So that's why it has been given as positive. So you should not think that only positively charged body exists. Okay, actually the charges present in the wire can also be negative also. So this is the positively charged wire now. So this positively charged wire has a linear charge density lambda. Okay, so it has a linear charge density lambda. Linear charge density of this wire is lambda, and from this wire you take a particular distance small r. Okay, so for calculating the electric field due to this wire, you have to imagine a cylinder or cylindrical shape around this wire. So the cylinder here is the Gaussian surface for this wire. Okay, so when you imagine a cylinder like this, so here you can see on these two surfaces, the electric field and the surface area vector are perpendicular to each other. You can see here. So this E is the electric field and this n cap is the unit vector of the surface area, because according to Gauss theorem, the integral is integral E dot ds only. So this is the dot product, and when you replace this surface area vector like this, so this n cap is the unit vector along the surface area. So when the electric field and the surface area vector is at 90 degree, since this is a dot product, the integral will vanish. Okay, so here along the two caps, the electric field and the surface area vector are perpendicular to each other, so the integral vanishes. But along the surface of the cylinder, both are parallel to each other, as you can see here. Both are parallel to each other, so the integral won't vanish. So from this, we actually calculate the electric field, that is given by lambda by 2 pi epsilon 0 r. So we are not bothered about the derivation part, since you all might have already studied the derivation part in your 12th grade. Okay, 12th grade in your school also, you might have discussed in detail. Okay, you might have studied in detail the derivation part. So here we are not bothered about the derivation part, but here we should know only the end result or the final result, so that you can straight away apply these results in your numerical problem. Okay, so this is the first application, and the second application is this. So here you have a sheet of charge. For this sheet of charge, the surface charge density is given by sigma, and from this sheet, when you take a point at a distance small r, so now you calculate the electric field. The electric field is given by sigma by 2 epsilon 0. Okay, so here also the Gaussian surface is a cylinder, but here when you take the two caps of this cylinder, the electric field vector and the surface area vector are parallel to each other. So they are parallel to each other, so the integrals won't vanish. only the integrals along the body of this cylinder will vanish, because there the electric field and the surface area vector are perpendicular to each other. So integral along the body of the cylinder vanishes. So the electric field strength at a distance r from the sheet, it is given by sigma by 2 epsilon 0. So here also we are not bothering about the derivation part, since you all might have already studied that. Okay, right. So now the third application, it is the uniformly charged sphere. Okay, it is a uniformly charged sphere, and here you can see the inner sphere. Okay, the inner sphere is actually the sphere which we are considering. This sphere, okay, this sphere is actually the sphere we are considering. It is having a radius capital R. Okay, the radius of this inner sphere is capital R. This is having a charges. This is having actually charges. So here actually I am denoting the charges plus. Okay, the charges are present on this sphere. This is actually the sphere for which we need to calculate the electric field, and the radius of the sphere is capital R. Okay, so from the center of the sphere, you imagine a point at a distance small r. Okay, you imagine a point at a distance small r, and at that point you need to calculate the electric field. For that, you need to consider an imaginary sphere that is given by this sphere. The outer sphere is actually the Gaussian surface. Okay, so Gaussian surface for a sphere is actually another sphere of radius small r. Okay, so you need to calculate the electric field at the distance small r only. So the Gaussian surface is actually another sphere having a radius small r. So now at this point, what is the electric field? It is given by, so E equal to Q by 4 pi epsilon naught into small r square. Okay, at a point outside the sphere, the electric field is given by Q by 4 pi epsilon naught small r square. So when you consider a point on the surface of the sphere, this expression is modified to this form. So here actually instead of small r, you have to write capital R. That is the radius of the sphere. Okay. And when you consider a point inside the sphere, the electric field will be 0. Okay. The electric field will be 0, since inside the sphere there won't be any charges. The electric field will be 0 inside the sphere. So this is how you need to calculate the electric field for a sphere uniformly charged. I hope you all understood this way. Okay. Right. So now we are moving on to the numerical problems. So here we are considering a square of side A lying in XY plane, such that two of its sides are lying on the axis. If an electric field vector E equal to E naught K x K cap is applied on the square, the flux passing through the square is. Okay. So here you need to calculate the electric flux passing through the square. They have given a condition: square of side A is lying in XY plane, such that two of its sides are lying on the axis. So if an electric field E vector E equal to E naught x K cap is applied on the square, the flux passing through the square is. So we need to calculate this thing. So first of all, let me draw a square. Okay, this is the square, and the side of the square is given by A. Okay, the side of the square is given by, so though it may look rectangular shape, this is actually a square. Okay, so let me redraw that again. Now it looks like a square. Okay, I think so. This is the square, and we need to calculate the electric field. Okay, the side of the square is actually small a. Side of the square is small a. It is lying in the xy plane. So here you have this y axis. Okay, so here you have this y axis, and here you have the x axis actually. So let me draw again. So here you are having the x axis. So here you have x axis. It is lying in the xy plane. So the square is lying here. The side is A, and an electric field E equal to E naught x k cap is applied on the square. Now we have to calculate the flux passing through the square, and the side of the square is actually A and A. Okay. So we need to calculate the flux. So for calculating the flux, we have to go for Gauss theorem. So integral E dot ds. Okay, integral E dot ds. So we have to apply this equation. So here integral E dot dx is nothing but dx into dy. Okay, dx into dy. I can also write it in a better way so that you can understand easily. So since it is lying in the xy plane, the surface area vector is given by this thing. So here let me write it here. So this is dx I cap into dy j cap. Actually, this is lying in the xy plane, so the surface area vector is given by dx into dy. So that is I dot j. Okay, that is I dot j. I dot j means actually we'll be getting k cap. Okay, so now here let me write it again. So E dot dx dy. Okay, so this is actually a double integral. So double integral, the integration limit is 0 to a because the side of the square is a, so 0 to a. So the electric field is E naught into x. This is dx, this is dy. So this I dot j is nothing but, okay, this I dx dy, actually you don't have to describe this I cap and j cap here. So that is implied only. So here this is dx into dy. So E dot dx dy, so that is E naught x into dx dy. So the integration limits are 0 to a. So E naught x dx. So now what I have to do is I have to apply the limits for dx and dy separately. The E naught is actually the constant, so that I can take out that constant. So let me erase this diagram, and then I can write the remaining steps here itself. Okay, so that you will understand it easily. So here I am continuing from here. So integral this E naught I am taking out as common. Integral 0 to a. So this is x dx, and integral 0 to a, this will be dy. Okay, when you integrate this, you will be getting E naught into, applying integration, you will be getting 0 to a. This is x squared by 2 actually. Okay, this is x squared by 2. So this is x squared by 2. Integral x dx is nothing but x squared by 2 plus sorry, not plus, it is uh, integral y. Okay, integral dy equal to y, so that will be y, and when you integrate that, you will be getting into y 0 to a. Okay, so this is now e naught into x squared by 2, right? So a squared by 2 minus 0 squared by 2, so that is 0 by 2, anything that is 0, so I am not taking it. So e naught into a squared by 2 into y. So there you have to apply the limit a and 0. So there you will be getting into a. So what is the final answer now? E naught a cube divided by 2 is your final answer. So this is how you need to find out the flux passing through the square. Okay, this is how you need to find out the flux passing through the square. So you have a square lying in xy plane, and you have its two sides lying on the axis. So if you apply the electric field E, vector E equal to E naught x k cap applied on the square, and you need to calculate the flux passing through the square. So for that, you have to apply E dot ds. So whenever you want to find out the electric flux, you have to apply this equation E dot ds, that is E dot dx dy. So the E is given by E naught into x. So I have written it here, dx dy, and then I have to apply the limits. The limits are 0 to a. So integral 0 to a x dx, integral 0 to a dy. So on applying the limits, I am getting E naught a cube by 2. That is option 2 here. Okay. So this is how you need to solve this numerical problem. If you have any doubt, you can ask at any point during the session. Okay. Right. So I am removing this annotation so that it doesn't disturb the next slide. Okay. So whenever you move on from one slide to another, this annotation also is carried over from one slide to another. So it will be a little bit disturbing to you. So I have removed the annotation. Okay. So for a square type of problems, you can use your Gauss theorem or Gauss law like this. Now the second problem, okay, you can see on this page. Figure shows a charge Q placed at the center of a hemisphere. A second charge capital Q is placed at one of the positions A, B, C, and D. So it actually, what they actually mean is the second charge capital Q can be placed at any one of the positions. Either it can be on this A, or either it can be at this point B, or it can be at the point D, or it can be at the point A, or even C. So already you have a charge small q here at the center of this hemisphere, and you can place a second charge capital Q at any of these positions, either C, A, B, or B. You can place this capital Q at any of these positions. So what they are asking is, in which positions of this second charge the electric flux through the hemisphere remains unchanged. So what they are asking is, at which position of this charge capital Q the electric flux through the hemisphere remains unchanged. That means the placing of this charge capital Q should not have any effect on the electric flux coming through it, because already you have this charge small q here. Already you will be having electric flux coming out through this hemisphere due to the presence of this charge small q. So this flux should not be disturbed by the presence of this capital Q. But where this capital Q should be placed, okay, so that it won't disturb the flux already coming out. Okay, so here you have the options, and from these options you should tell what is the position of this second charge capital Q, so that the electric flux is undisturbed. Now can anyone tell me what is the answer for this question? By little bit common sense and the Gauss theorem, you can easily tell the answer for this question. Can anyone tell me? You can unmute yourself and talk. No issues. At which positions the charge capital Q should be placed so that the electric flux through the hemisphere remains unchanged? You can unmute yourself and you can talk. You are free to talk, students. You are free to talk. You can unmute yourself and you can talk. You can answer the question also.
Sir, I think third, A and B.
A and B. You have to give reason for that too. So,
Sir, it is a outer
Ah.
of the semisphere, sir.
but
The point is outer side of the semisphere.
but the point B is also outside the hemisphere, and the point C is also outside the hemisphere.
So when you draw the rays towards the hemisphere, sir,
Okay.
At the center of the cube,
Okay.
it can passes the rays, sir. Flux.
Electric flux.
Yes, sir.
Okay, good try, but option 4 is not the correct one.
Sir, option 3.
Option 3 is all not the correct one actually. So
Okay.
any others can any other answer from you people? Actually,
A and C, sir.
pardon?
A and C.
Which is the option you are telling actually? The option number, can you tell me?
Option
Option?
A.
The first option you are telling, right? Student?
Yes, sir.
Yes. So the first option is actually correct, because when you take the integral E dot ds or the flux, okay. So since the charge is placed here, and when you place the charge capital Q here, okay, the electric field due to that charge and the surface area vector, it will be actually perpendicular when you place this charge capital Q at these points, okay. When you keep the charge capital Q here or here, then the area vector and the electric field won't be making 90 degree, okay, won't be making 90 degree. So then the charge capital Q will have some effect on the electric flux through the hemisphere. So for these positions B and D, whenever you keep the charge capital Q, okay, that that positions will actually disturb the electric flux coming through the hemisphere, okay. But when you place them here at A and C, then the electric field due to that charge capital Q on this surface area vector, it will be at 90 degrees. So the total flux due to that charge capital Q will be 0, and only the total flux due to this charge small q, okay, will be there, okay. So this is how you need to understand this problem, okay. This is how you need to understand this problem. So the correct option is the first one, option A and C, right. So now let us move on to the next problem or next question. Here you see figure 1 shows an imaginary cube of edge L by 2. A uniformly charged rod of length capital L moved towards left at a small but constant speed v. At t equal to 0, the left end just touches the center of the face of the cube opposite. So which of the graphs shown in figure 2 represents the flux of the electric field through the cube as the rod goes through it? So this question is a little bit lengthy, but you have to understand the question first. So you have an imaginary cube of edge L by 2. That means the side of this cube is L by 2. And here you have a uniformly charged rod, okay. So the uniformly charged rod is this thing, okay, this thing. The length of this rod is actually capital L. It is moving with a velocity or speed small v, okay. and this rod is actually moving towards the cube, and it is moving with a constant speed v. So at time t equal to 0, the left end just touches the center of the face of the cube. Okay, and after a few minutes or few seconds, the rod actually goes through the cube and it comes out through the other side. Okay, the scenario is very simple. You have an imaginary cube here and you have a rod of length capital L. It is moving with velocity small v. So this rod actually moves inside the cube. Okay, this rod actually moves inside the cube, and it is touching this face, and it is actually coming out through the other part of the face, other face of the cube. So what they are asking is, they have given you a graph and they have plotted the time along x-axis and flux, electric flux due to this rod along y-axis. Okay, the electric flux through this cube due to the entry of this charged rod has been depicted in these graphs. So here you have 4 curves. Okay, so this blue color one is A, and this B, this green color one is B, and this one is C, and this one is D. The time along x-axis and the electric flux through the cube along y-axis. So now you have to give the correct option. So which graph, okay, which curve actually, which curve of this graph represents the flux of the electric field through the cube as the rod goes through it? Any guesses, students, or any answer from your side? Can anyone tell the answer? So you have to understand the question first. This is the cube and a charged rod enters this cube. Okay, at time t equal to 0. So from that point, the rod actually goes inside the cube and it comes out through the other face of the cube. So what is the electric flux through this cube due to the presence of this charged rod? Okay, and they have given you 4 curves, A, B, C, and D. The blue color one is the A, and the green color one is B, and the brown color one is C, and the red color one in the form of trapezium is D. Okay, which of the 4 options represents the flux of the electric field through the cube? Can anyone tell the answer? Or you can even make a guess, no issues. Even if it is wrong, then no issues.
So,
So
Yes,
C.
tell me.
I'm not sure, sir, but is it D?
Option D. Okay. Another student told it
So
is
C.
answer C. Okay. Can you explain that? Even
Sir,
if it is, yes, yeah, tell me, please.
Sir, even in the graph,
Okay.
the line is passing towards
Okay.
flux, sir. The C is passing towards the flux arrow, sir.
Okay.
So I had guessed the C, sir.
Okay. That is your guess, right? And another student told it is option D. So that student, can you explain that?
So, I thought that just so like there might be so since the rod has a charge and it's moving with constant speed and it enters the imaginary cube. I thought that I just guessed that it might be D, sir.
Okay. Okay. So actually, the correct answer for this question is option D. So why it is so? So let us see the explanation. So initially, when the charged rod enters this face of the cube at time t equal to 0, okay, there is no electric flux. Okay, there is no electric flux, so that is 0. The electric flux here is 0. And when the charged rod starts entering the cube through this face, the electric flux through the cube actually increases. Okay, since the charged rod actually enters the cube, the electric flux through the cube actually increases. Okay, so that's why you have the graph pattern like this. Here, as time goes on, the flux is increasing. Okay, as you can see, this portion of the graph, it tells you that as time goes on, the electric flux through the cube increases because the uniformly charged rod enters the cube. Okay. Once the charged rod is completely inside the cube, then the electric flux remains constant. Okay. Then the electric flux remains constant as long as the charged rod is inside the cube. So after a certain period of time, the charged rod actually comes out through the other face of the cube. Okay. So when it does, what happens is the electric flux through the cube decreases because the charged rod is moving away from the cube. So the electric flux actually falls down or decreases. So the graph pattern is like this. So initially the electric flux is actually increasing due to the entry of this charged rod inside the cube, and once the charged rod is completely inside the cube, then you will be getting a constant electric flux through the cube because the charged rod is there. So once a small portion of the charged rod actually exits the cube, okay, at that time the electric flux starts decreasing because the charged rod is moving away. So slow and steadily, when the rod actually moves out of this cube, then the flux is actually decreasing. So the graph pattern is like this. So option D is the correct one. Okay. Anyway, good try from you students. So you should not bother about whether it is right or wrong, and you have to interact and you have to think. Okay. Then only you can learn something. So actually, I appreciate the students who tried to answer the question. So other students also, you can learn something whenever you see a numerical problem. You always try to learn. Okay. So in this way, you will be able to master the concepts, and you will be getting a good command to solve the numerical problems in physics. Okay. So I think the time is up now. So I will stop sharing my screen. And does anyone have any doubt in today's
Excuse me,
class?
sir.
Yes, yes.
Sir,
Please.
if it is a triangle, sir,
Okay.
the flux is passing through it, then it is also an option D, sir.
Yes, actually the concept is same. So what is the concept here? Actually, when you take the rod inside the cube, the electric flux starts increasing. Okay. Once the rod is completely inside the cube or even the triangle, then at that time the flux remains constant. Once your rod moves out of the triangle, then the flux starts decreasing. So what is very important here is that whether the charged rod is inside the particular surface or outside the particular surface, that is important. So once you take a cube and the charged rod enters the cube, then the flux due to the charges present in the rod actually starts increasing. Once it is completely inside your surface, whether it is cube or even triangle, so whether it is completely inside the cube or even triangle, then when it is completely inside, then the flux remains constant. And when it moves out of the figure, whether it's triangle or cube, then the flux starts decreasing. So this is why we have the option D there. Okay.
Okay, sir. Thank you.
Okay. Okay. In case
Thank you, sir. Thank you,
okay,
sir.
ma'am. Okay, ma'am. Thank
Please,
you so
children.
much, ma'am.
Yes, thank you, sir. Thank you, sir. Children, please join in biology link.
Yes, ma'am. I am making you the host of this session.
Yes, sir. Please, sir.